Hi, everybody out there in chemistry land. Today we're going to be talking a little bit about some of the experimentation and theory behind the Bohr model of the atom that produced the idea that electrons resided in energy levels. And so Bohr's theory was originated from some experimentation he did where he was heating elements up to the point of their incandescence. Basically, what that means is that he was heating elements up until they started to glow. And he noticed that if he took the light that was coming off of a glowing element and he put it through a prism, that he got a unique set of very specific line spectra colors for that element. Now, there's a few different ways that you can accomplish this. Say you had some hydrogen gas. If you put some hydrogen gas in a tube that doesn't have any oxygen in it and run an electric current through that tube, you can get the hydrogen gas to start to glow, kind of like a fluorescent light bulb. But when that light that was coming off of that pale blue tube was put through a prism, he noticed that four very specific colors were coming out of the hydrogen. And as he experimented with other elements, he noticed that pretty much every element had its own unique fingerprint spectrum of colors that would be released. So an atomic emission spectrum is the unique set of colors that is released when atoms of particular elements are excited and then start to give off light. And so that got Bohr thinking about what's going on inside the atom that could be producing this. So we'll get into how that evolved a little bit. Okay, now it's important that you understand that visible light, the light that we can see, only makes up a very small fraction of a larger electromagnetic spectrum of radiation. And really, the thing that's different about different forms of electromagnetic radiation is the wavelength, the frequency, and the energy. If you get really long wavelengths, you might be talking about radio waves. If they get a little bit shorter, you might get into microwaves, onto infrared, visible, ultraviolet, X-ray, and of course the shortest wavelengths of all are gamma rays. And if you kind of compare the frequency and wavelength and energy on this spectrum, this end of the spectrum, of course, has the long wavelength, whereas this end of the spectrum has a short wavelength. This end of the spectrum, because the wavelength is long, the frequency is going to be the opposite. Okay, so if you have a long wavelength, a large wavelength, then you're going to have a small frequency. And to kind of explain why that's the case, if you think about what frequency is how many waves would pass by a fixed point. So you can imagine, say I have this fixed point and this whole wave is just moving this way, how many peaks go by that fixed point in a given amount of time, usually 1 second, would be considered to be the wavelength. And since all of these move at the same speed, then pretty much the shorter the waves are, the more wavelengths are going to go by a fixed point and the higher the frequency. The longer the wavelength would be, then the shorter the frequency would be. So this end is going to have a small frequency. This end would have a high frequency. And frequency and energy are also directly related. You can also think about frequency as being how quickly the wave oscillates. And if the wave is oscillating faster, then that's going to be a higher energy. So if you've got a small frequency, then you also would have a low energy. Okay, as opposed to over here on this end of the spectrum, energy gets higher. Okay. Now, if you examine just the visible spectrum, you can say the same thing with different colors of light. The red end of the spectrum would have the longest wavelength, the smallest frequency, and the lowest energy of all the colors that you can see. And the opposite would be true for the violet end of the spectrum. The violet end of the spectrum would have the shortest wavelengths. It would have the fastest frequency, and it would have the highest energy of all of those colors. There's an old acronym that you can use to remember the colors of visible light from longest wavelength to shortest wavelength, and that is ROY. It's kind of like a name. ROY. G. BIV, which stands for red, orange, yellow, green, blue, indigo, and violet. I think I saw on some publication that indigo is not technically its own color now or whatever, but whatever. There you go. It helps you remember the colors in order from longest wavelength to shortest wavelength in the visible light spectrum. Okay? Now, why is this important? Well, if we, want to get into, why are certain colors released by certain elements, and how does that happen? Why, for instance, did hydrogen release these very four specific colors? Bohr came up with this model or this theory to explain what was happening there. Okay, because he noticed that different elements were giving off certain colors, and here's some examples of some line spectra of some different elements, and we've recorded line spectra for pretty much all of the known elements there. He was saying that these colors were released when electrons were falling down from a higher energy level to a lower energy level, and it was the transition between energy levels that was causing this. Now, since every atom had a different number of protons in the nucleus, that caused every atom's energy level size to be of unique sizes and distances from the nucleus. So every atom had its own unique way that those electrons could fall from higher energy levels to lower energy levels and give off those unique colors. Now, I know that's a lot, but so let's kind of break that down a little bit more. So a couple of key terms that kind of go along with this process here. You can say that electrons surround an atom, or electrons that surround an atom can absorb a discrete packet of energy called a photon. You can think about a photon as a particle of light. Einstein said that light has this wave-particle duality, but the smallest piece of energy, of electromagnetic radiation that you can have is a little packet of energy called a photon. Now, if the electron takes in that photon, it's going to become excited. And basically what that means when we say excited is that it moves to a higher energy level. So, you can imagine this electron that's going around the nucleus of the atom. When this photon comes in and gets the electron jumps out so that it's further away from the nucleus. Now, when excited electrons lose that extra energy, they're going to fall back down to the lowest energy level that they can reside in. That lowest energy level is called the ground state. It might be energy level 1, but it doesn't have to be. It's just the lowest energy level that electron can fit into. And there may be other electrons already in the lower energy levels that are keeping those levels full. So whatever the lowest energy level the electron can go back to is the ground state. Now, every time that electron falls back down, it's going to release light of a very particular color. And so that photon is going to come off and carry with it a very specific amount of energy that corresponds to a very specific frequency and wavelength. Therefore, it's going to be a unique color. And so because every element has uniquely sized energy levels based on the number of protons that are in the nucleus, that is going to give every single element its own unique spectrum of those possible colors that can be produced when electrons fall from higher levels back down to lower levels. Okay? To kind of visualize this a little bit better, let's use a picture here. Let's use a model. Okay, so you can imagine we got this electron. It's in the lowest energy level when this process starts, and let's say that this photon comes in and this electron picks up this photon. After the electron picks up that photon, the electron is going to move up. It's going to jump up to the next energy level. Okay, so maybe it jumps up to the higher energy level, and maybe now it's, going around the nucleus up here in this higher energy level. If that happens, that electron is in an excited state and has picked up the extra energy. Now that can't stick around for very long, so that electron is going to then quickly fall back down to the ground state, or at least to a lower energy level. And in the process, when that happens, that photon of light is going to come back out of that electron and be released as maybe visible light when you see that. So to recap, the electron picks up the energy, picks up a photon, jumps up to the excited state, and then releases that energy and falls back down to the ground state and releases that light in the process. Now, if you go back to, hydrogen here and wonder why, hey, so how could you explain that hydrogen releases these very four specific colors? When you're looking at a model of hydrogen, it's super simple. There's one proton and one electron in a hydrogen atom, okay? Well, imagine for a second that, and you'll have to deal with my terrible circle drawing. Imagine you've got this hydrogen atom and you've got, these energy levels outside the middle of the atom. The electron, depending on how much energy it is given, could fall from higher levels back down to lower levels. Okay, so let's suppose that the electron falls from energy level 1 just down to energy level 2 down to energy level 1. Okay, that's a low level transition. Well, that's not a big energy gap, and so if that happened, then maybe the electron released a red photon, which is the lowest energy photon. Okay, if the gap where the electron fell down was a little bit larger, then you might produce a photon that had, a little bit more energy. So if it fell from, say energy level 3 down to energy level 1, then that might release a green photon. If you had an even larger gap in, the energy than when the electron fell from maybe the fourth energy level all the way down to the third energy level, that's a bigger energy gap. And so the photon that comes off is going to be higher frequency, higher energy, and it might release a purple photon in that transition, or a violet photon, I guess would be better to say. Okay, so even though hydrogen only has one electron, it can still release multiple colors because there's multiple transitions that can occur within the same atom with that electron falling down from, a few different combinations of higher energy levels to lower energy levels. And that was able to help explain why, even though hydrogen's got only one electron, it can produce these four specific colors. Now, hydrogen may be able to produce more different wavelengths or frequencies of electromagnetic radiation, but apparently these are the only four that fit into the visible light spectrum. So if you had, an electron that was super far out and it fell down, then you may have, an ultraviolet transition, but, you're not going to be able to see that. Okay. So it's important to understand that some of these electron transitions can produce radiation that is not visible to the naked eye, simply because it's not in the visible light spectrum. Okay? All right, so that is the theory behind, or at least some of the experimentation and explanation behind the idea of energy levels in Bohr's theory and Bohr's model of the atom. Until next time.